Right now, an object that was never born in our solar system is racing past Mars at roughly 86 kilometers per second, more than 190,000 miles per hour, shedding an estimated 1 ton of dust into space every single second. It has no orbit around our sun. It came from somewhere else entirely, passed through our solar system once and is already leaving forever. And when a Chinese spacecraft happened to catch it on camera from an angle no telescope on Earth has ever managed, what it found didn't just confirm what scientists expected, it contradicted it. Let's start with the numbers because they explain why this object has scientists this interested. This is 3I Atlas, only the third interstellar object ever confirmed entering our solar system, after Oumuamua in 2017 and 2I Borisov in 2019. It was first spotted on July the 1st, 2025, by the NASA-funded Asteroid Terrestrial Impact Last Alert System, a survey telescope in Rio Hurtado, Chile, moving at around 58 kilometers per second, fast enough that scientists quickly determined it wasn't following a closed orbit around our sun at all. It was just passing through on a hyperbolic trajectory that will carry it back out into interstellar space and never return. Here's the part of this story that almost no coverage explains properly, and it's the part that actually matters. China's Tianwen-1 Orbiter, a spacecraft built and launched to study Mars, not comets, happened to be in exactly the right position to turn its camera toward 3I Atlas as it swept past the red planet in early October 2025. And because Tianwen-1 was viewing the comet from an angle wildly different from every telescope on Earth, it saw something that directly contradicted earlier reports from some of the most powerful observatories in the world, including Hubble. If you want to understand exactly what China's Mars Orbiter found and why it's rewriting part of what scientists thought they knew about this interstellar visitor, that's exactly what we're breaking down today. I'm the host here at Today's Latest Analysis, and we go straight to the actual published research, not just the exciting headlines. Subscribe now, because with an object moving this fast and this rare, updates could come at any time. Now let's start from the beginning, because to understand why this particular observation matters, you need to understand just how rare an object like 3I Atlas actually is. For nearly the entire history of astronomy, every comet and asteroid we've ever studied was born somewhere inside our own solar system, orbiting the sun the same way Earth does, just on a different path. Interstellar objects are different. They form around other stars entirely, sometimes flung out of their home systems by gravitational interactions with planets billions of years ago. And then they drift silently through the emptiness between stars for unimaginable stretches of time before, by pure chance, one of them happens to pass close enough to our sun for us to notice it at all. The first one we ever confirmed, Oumuamua, was spotted in 2017, and its strange elongated shape and unexplained subtle acceleration sparked genuine scientific debate, and a wave of public speculation about whether it might not be a natural object at all. The second, 2I Borisov, arrived in 2019 and behaved much more like a typical comet, with a visible tail and coma, reassuring most scientists that these visitors, while rare, aren't fundamentally mysterious in nature. 3I Atlas is only the third confirmed object of this kind ever detected, which is exactly why space agencies around the world scrambled to get any instrument they could point it at it during its brief pass through our neighborhood. Here's where Tianwen-1 comes in. China launched the Tianwen-1 mission in July 2020, and it entered orbit around Mars in February 2021, going on to deploy the Zhurong rover onto the Martian surface that same year. The orbiter itself carries a high-resolution imaging camera called HiRIC, a 512 by 512 pixel CMOS imager originally designed for one job, photographing the brightly lit surface of Mars in detail. It was never built to track a faint, fast-moving object drifting through deep space. But when 3I Atlas made its close approach to Mars in early October 2025, Chinese mission scientists saw a rare opportunity and repurposed the spacecraft's camera for something it had never attempted before: direct deep space astronomy from Mars orbit, the first observation of its kind in the mission's history. The technical challenge involved is worth appreciating on its own. From Tianwen-1's position, roughly 30 million kilometers, about 18. 6 million miles from the comet 3I Atlas, appeared somewhere between 10,000 and 100,000 times fainter than the sunlit Martian surface features, the camera was actually built to photograph. The team carefully trained HiRIC on the comet across 3 separate observing windows, September 30th, October 1st, and October 3rd, capturing 57 individual 30-second exposures in total. Because the comet was moving at nearly 86 kilometers per second relative to Mars during this period, the viewing geometry shifted noticeably even across those few days, meaning each set of images captured the comet's dust cloud in a slightly different configuration. Now here's the second layer of this story, the part that makes this observation genuinely valuable rather than just a nice photo opportunity. Every previous observation of 3I Atlas, whether from ground-based telescopes or from instruments in Earth orbit, had to view the comet from roughly the same general direction, essentially looking at it from Earth's vantage point in the solar system. Tianwen-1's position at Mars put it significantly outside the comet's orbital plane, giving scientists their first genuine look at 3I Atlas from an entirely different angle. As the research team, led by astronomer Shinrin, put it directly in their published paper, this observation provided a unique constraint on the dust dynamics around the comet, something no Earth-based instrument could offer, no matter how powerful it was. And what that new angle revealed was surprising in more than one way. First, the dust itself. By comparing the images against standard dust dispersion models, researchers found that the coma, the glowing cloud of gas and dust surrounding the comet's nucleus, was dominated by unusually large particles, roughly 1/10 of a millimeter to a full millimeter across, essentially the size of coarse sand rather than the fine, smoke-like grains typically expected in a comet's tail. Those heavier grains were also moving remarkably slowly once ejected from the nucleus, drifting away at only about 3 to 10 meters per second, a slow, steady release rather than a violent one. Combined with the total dust output, the team calculated 3I Atlas was shedding material at a rate of roughly 1,000 kilograms per second, about a ton of dust every single second, far higher than earlier ground-based estimates that had put the figure at only tens of kilograms per second. But the most genuinely unexpected result wasn't about how much dust the comet was releasing. It was about what wasn't there at all. In the months before Tianwen-1's flyby, other observatories, including Hubble, had reported the presence of narrow, distinct dust jets, tight streams of material erupting from specific points on the comet's surface, likely connected to its rotation. When the Chinese team examined their own images, captured from a dramatically different viewing angle, they searched specifically for those same jet structures. They found none. Instead, the dust cloud in Tianwen-1's images appeared smooth and fan-shaped, with no discrete streaks anywhere in the data. In their published paper, the researchers wrote plainly that they searched for jet structures but found none, and went further, stating that if those previously reported jets were genuinely real, they should have shown up in Tianwen-1's data from its very different vantage point, and they simply didn't. That's the finding worth sitting with for a moment, because it isn't a minor technical footnote. It's two respected sets of observations, using different instruments from completely different positions in space, producing genuinely conflicting pictures of the same object's structure. Science doesn't usually resolve disagreements like that instantly. It resolves them over months and years, as more data comes in from more angles, which is exactly why an unplanned observation from an orbiter built for an entirely different mission turned out to be so valuable here. This naturally connects to the wider conversation swirling around 3I Atlas since the moment it was discovered. Because it's only the third interstellar object ever confirmed, and because the first one, Oumuamua, generated genuine scientific debate about whether it might be artificial rather than natural, some of that same speculation attached itself to 3I Atlas almost immediately, with a handful of researchers and plenty of online commentary asking whether this newest visitor might not be a comet at all. Here's the direct, evidence-based answer to that question. Every independent measurement collected on 3I Atlas, its coma, its tail, its dust output, its chemical composition, points toward an entirely natural origin. NASA's James Webb Space Telescope examined its chemistry directly and found an unusually high ratio of carbon dioxide to water compared to nearly every comet we've ever studied that formed inside our own solar system. But unusual chemistry is not evidence of anything artificial. It's evidence that 3I Atlas likely formed in an extremely cold environment far out in its home system, where different ices condense than the ones we're used to seeing closer to our own sun. Researchers studying it directly note that this comet shares its unusually large dust grains and heavy volatile content with 2I Borisov, the previous interstellar visitor, suggesting both objects formed under similar frigid conditions on the outer edges of entirely different planetary systems. A pattern, not an anomaly. So here's what actually matters coming out of this observation. It's not evidence of anything artificial, and it's not a sign that something dangerous is approaching Earth. 3I Atlas's trajectory has been tracked closely, and it poses no threat to our planet. What it genuinely represents is a case study in how much a single new viewing angle can change our understanding of an object we thought we already had a handle on. The dust grain sizes, the ton per second mass loss rate, and especially the absence of jets that other telescopes reported, are all pieces of a more complete, more accurate picture of what 3I Atlas actually looks like up close, one that simply wasn't available until an operational Mars orbiter happened to be in the right place at the right time. There's also a broader lesson in this for how space agencies think about their existing hardware. Tianwen-1 was never designed or funded as a comet hunting mission. It's a Mars orbiter, full stop. But the research team behind this discovery explicitly framed their success as proof of concept, writing that it demonstrated the capability and flexibility of operating spacecraft to perform what astronomers call target of opportunity observations, essentially redirecting existing missions toward rare, unplanned events rather than requiring an entirely new, purpose-built spacecraft every time something unusual passes through the solar system. The European Space Agency's Mars Express and ExoMars Trace Gas Orbiter both did something similar around the same time, also capturing their own images of 3I Atlas as it passed. That means for the first time, multiple operational Mars missions, built for entirely different purposes, ended up functioning as a makeshift network of comet-watching outposts scattered across the inner solar system, simply because they happened to already be there when something rare came through. There's one more detail from the published research worth understanding, because it shows just how carefully the Chinese team had to work with equipment that was never meant for this job. Hyric wasn't just aimed and left running. Because the comet was so much fainter than anything the camera was designed to capture, researchers had to stack all 57 individual 30-second exposures from each observing session together just to pull a clean signal out of the background noise, then apply a specific brightness correction technique to separate the comet's faint glow from the star trails and sensor artifacts that show up in any long exposure image taken from a moving spacecraft. Even after all of that processing, the team could still measure how the coma's brightness fell off with distance from the nucleus, finding it dropped off sharply near the center and then leveled out further away. Exactly the pattern you'd expect from large dust grains steadily streaming outward under the gentle push of sunlight, known to scientists as solar radiation pressure. That consistency across all three observing sessions, even as the viewing angle shifted day to day, gave the researchers real confidence that what they were measuring reflected the comet's actual physical behavior, not some artifact of the unusual instrument being used to observe it. It's also worth understanding what this means for the object 3I Atlas is being compared against, most often, its predecessor 2I Borisov. Both interstellar comets have now shown the same unusual combination: oversized dust grains and a chemical makeup rich in easily vaporized compounds called supervolatiles, the kind of ices that only stay solid in extremely cold environments. Researchers studying both objects argue this shared signature likely points to where these comets actually formed, not close to their home stars where it's warm enough for smaller, finer dust to dominate, but out in the frozen outer edges of their planetary systems, in regions similar to our own solar system's distant Kuiper belt. Finding that same pattern twice in two completely unrelated interstellar visitors arriving 8 years apart is exactly the kind of repeated evidence that turns a single strange observation into a genuine scientific pattern. If space agencies increasingly treat their existing orbiters as flexible, reproposable instruments rather than single-mission machines, the next Oumuamua, Borisov, or Atlas-style object won't just be photographed from Earth. It could be observed simultaneously from multiple points scattered across the solar system, each offering its own unique angle, the exact kind of multi-perspective view that just revealed 3I Atlas was shedding a ton of dust a second, in grains the size of sand with jets that may never have actually existed at all. 3I Atlas is still moving away from us right now, heading back out into the depths of interstellar space, carrying whatever secrets it hasn't yet revealed with it, on a journey that will likely never bring it anywhere near our solar system again. It arrived from somewhere else, passed silently through our cosmic neighborhood for a matter of months, and in that brief window, an orbiter built to photograph the dust and rock of Mars ended up rewriting a piece of what we thought we understood about a visitor from another star system entirely. I'll bring you the next update the moment new data comes in on 3I Atlas, or the moment any agency announces plans for the next target of opportunity observation like this one. If you want real space discoveries explained accurately, without the exaggeration that usually comes with headlines about interstellar objects, that's exactly what we do here every time research like this gets published. Drop a comment and let me know what surprised you most, whether it's the missing jets, the ton of dust per second, or the fact that a Mars orbiter pulled this off at all. Subscribe so you don't miss the next update, share this with anyone who'd find it genuinely fascinating, and I'll see you in the next one.